Welcome, good morning. Welcome to OPN207. Sorry, my voice is a little hoarse, so at least with the headphones, you'll be able to hear me clearly. OPN207, sorry, here we go. Particle, one query language for all your data. My name is Alman. I'm a principal engineer with E-commerce Foundation Technologies, which is a platform, we own the platform technologies that power some of the retail website. And I'm co-presenting with Dr. Yannis Papakonstantinou, senior principal scientist with AWS, Amazon Redshift. So today, oops, apologies. Oh, there it goes, sorry. Getting used to this setup. So today I'm going to start by talking about what Particle is and sort of explain a little bit of the background about how it came to be and some of the problems that we observed and wanted to solve with it. And then I'm going to walk through the tenets of what defines Particle as a query language as a way of introducing the key beliefs that we think make it actually solve these problems. And then following that, I'll turn it over to Yannis to give you a walkthrough of the Particle data model, as well as the Particle query language, which will give you some concrete examples and illustrate how the query language works. And finally, I will be discussing Particle open source, basically how you can use and contribute to the Particle ecosystem, and talk a bit about how we want to build the community with Particle. So at first I thought we weren't able to do Q&A, but it looks like we can do Q&A in this format, but we also have a chalk talk that's more interactive and whiteboard oriented in OPN308. And we also have a builder session that will actually take the open source implementation and let you hands-on extend it to support a different use case. So let's begin with what is Particle. A few years ago, in the retail side of things, we took a step back and it was pretty clear that there's a lot of diverse data sources. So the retail customer has not only AWS resources, but also our own internal storage systems and database engines. And there's a common theme here is we had not only document-oriented databases, document-oriented systems like Ion, JSON, that sort of thing, where the schema is loose and fluid, more flexible to solve for business use cases, but also we have traditional relational stores, particularly in our data warehouse, where report writers are targeting more simplified views of the data to generate reports. A clear example of this is the product data and the ordering data. Those are nested Ion documents. They're similar to JSON. And to get that data into the data warehouse, we actually have people to transform those into relational tables. And a clear customer need was developing because customers of the data warehouse were familiar with SQL, and we had a custom transformation language that transformed this here, and people were wanting to, our customers, internal customers really wanted us to provide a consistent interface across these things. Over on AWS a few years back, S3 was looking to add query to their object store. And in that case, they really wanted to be able to let their customers query the data without schema being required. And furthermore, Redshift Spectrum was also looking at adding query into the data lake, which again, they wanted to add into a SQL database the extension to the data lake where you can access nested data and provide flexibility around schema. Near this time, Amazon QLDB, Quantum Ledger Database, was being designed and implemented to be a brand new purpose-built document-oriented database using Ion, and they also needed a query language that was familiar to their customers. So this led us to reach across the organization, and I worked with my colleague here, Yannis, and also distinguished engineer in retail, Chris Suver, to really think back, take a step back and say, how do we want to solve this problem? There's a lot of use cases that seem similar, but different enough. Can we actually address that? Yannis here worked with at UCSD to develop SQL++, which has theoretical foundations and extensions to SQL to support nested and semi-structure. And we combined that with the work we were doing with SQL on Ion and retail to really combine and get the syntax figured out, sorted out, and build a reference implementation that we then open source, that we will then have open source. And that implementation is important because it allowed us to do a couple things. It allowed the service owners to actually play with this query language and start to learn and understand and dive into it. But it also gave them componentry to accelerate integrating Particle into their platforms. So taking a step back again, we saw there's many other languages out there, right? And this is not, there's a lot of text on this slide, I realize that. The goal here is not to memorize the text, it's just to demonstrate that there's a lot of different ways to say essentially the same thing, with SQL being kind of at the top left corner here. And so the thinking here was, do we really need to have different syntaxes for saying the same thing? And the work we did, I think, demonstrates that we don't. We can have a unified syntax here. So let me start with the tenets of Particle. One of the key tenets is unifying query language and data model. So what that means is we're not tying the query language to a particular format per se. So a lot of these extensions to query languages or query languages out there tend to tie to a particular language or a particular format such as JSON or CBOR. But in this case, we believe we have a data model, a type system that Yannis will cover in detail that really covers the type space of all various data formats and can be used the same way as you would on normal database tables. The other key important part of this tenet is storage independence. We want to make sure that we can use this query language across different database engines and storage engines and not be encumbered by particularities of each of those things. So just an example here about format and storage independence is we have a very simple table in the top here that has some scalar integers in them and some numbers. This simple query should operate the same way as it does on a similarly JSON or ION-based S3 object that has the same shape of data. This, again, is the kind of consistency that we saw customers asking for. This is a quote from one of our distinguished engineers. One thing that was very apparent and kind of goes back to the previous slide is we do have a lot of custom transformation languages within the retail space, or and we noticed one common thread. Customers really kept on asking us, we'd like a SQL-like language, please, to have it, to have it be more accessible to them. And so a really key thing for us is that Particle be SQL compatible. A lot of different languages start off away from SQL, but they tend to come back because there's a lot of customers that really understand it, and we want to leverage that customer user base. So again, kind of going back to the previous example, any places that a SQL query ought to work, Particle should work too. And that also means some of the baggage of SQL as well. We really strive for that compatibility, and SQL-like languages tend to forgo some of those in the name of simplicity. And although it is tempting to do that, I think it's important to maintain this compatibility because it really gives a good story for traditional databases to evolve to support new query capabilities for your data. Another key tenet for Particle is nested and semi-structured data. So what I mean by that is really we have a lot more document-oriented data out there, and we want to be able to access that document-oriented data the same way we would access relational tables. So a key part of that is making all that nested data work the same way as other kinds of data. SQL traditionally has two classes of data, the table, the relation, and the scalars within them, and you have a lot of incongruency where these two things match. Particle's semantics and syntax go out of its way to unify those things, so we generalize on that. On the part about semi-structured data and schema optionality, what does that actually mean? If you're coming from a more programmer-oriented background, you can think of this like dynamic typing. So traditional SQL is statically typed. The types are defined by schema, and they have to be known at compile time. Particle really gets into the mode of supporting all types at runtime, and this is especially evident in things like data lakes, where the data is piles of ION or JSON that you may not have a strong or strict schema over. Another key thing about schema is that it's optionality. So Particle enables us to have dynamic typing, but layer static typing as appropriate. This is really good for a lot of customer use cases, especially those of you who might be using document-oriented databases, because you can start with a pretty loose schema with the documents, the power of documents. And then over time, as the business and the application matures, you can ratchet that down and add more schema to that to restrict the application. Now, we want to make sure that the queries actually work as that spectrum of evolution happens. And again, Yannis will talk to that a little bit more later. Finally, we have a final tenet here that's not necessarily evident in syntax, but it's all about minimal and composable extensions. Every time we add syntax, you have to make sure it works with the rest of the system. So we really try our best not to do too much syntax extensions with Particle. We do the minimum we can, and there's a couple reasons for that. We want customers to be able to use this query language without extra cognitive overhead, but also you want to make sure that the syntax doesn't play with other parts of the system or semantics don't collide in other places. So this is evident in the kinds of extensions where flattening, for example, flattening nested structure looks like joins. They're the same. There's the same feature. Again, Yannis will talk through that in more detail. So finally, kind of the test of this thesis is where is Particle these days? Well, it started off years ago. Amazon Redshift when it looks for data lake integration, it uses Particle. It's still SQL and it still requires schema, but it allows you to get at that nested data. So they're a version of Particle that's schemaful. Another area that we work really closely with the S3 team is Particle there. They have a limitation of restricting it to a single object scope. But again, customers didn't even realize they were using Particle because it was just SQL syntax without schema, incidentally. And the other area is Amazon Quantum Ledger Database, where they use their components to get started and have their own query planner to take the syntax tree, but use pieces of the open source product to actually evaluate. And other than that, we have Amazon.com as well. So internal to the retail side of things, we have DataPath, a view materialization view that's adding Particle support from their legacy transform engine. We have data warehousing support for transforming streams of data, as well with a system called Cradle and Dryad. And we also have a system in Amazon fulfillment technology called OatsDB that adds some of this, add Particle as a first-class citizen as well. So there's more announcements forthcoming that we can't talk about here, but I think it's really exciting to see Particle in a vast, diverse areas, serving different customer needs in a consistent way. And I think there's a lot more to come in this space. So with that, turn it over to Yannis.
Thanks, Arman. So let's start our walkthrough in Particle with the goal of understanding the basics of the data model and the query language, and also making clear what we meant with the tenets of nested data as first-class citizen, the tenet of minimal and composable extensions. Okay, so let's start with the data model. So you may think of the Particle data model as being equal to Ion. In case you don't know Ion, you may think of it as JSON plus strong types. What you see on the board at this point is an instance of a Particle value. Okay, there is a bunch of, you will see that the syntax follows the JSON syntax, but do not think of Particle as a serialization format. Rather, Particle is a logical specification of values and types, rather than a particular string serialization. We use the JSON simply because it is the JSON syntax simply because it is known to many of you. Okay, so when it comes to comparisons with JSON, what is interesting to note here? Well, the green point, you see a time attribute and its value in green. What we want to say there is that this value that you see there is not a string. This is a typed value. It is a timestamp. Okay, we have not indicated here with a particular syntax that the type, but this is the meaning. There is one more addition to the JSON type system, and this is the addition of bugs. Many of you know already that mathematically an SQL table is a bug, which basically means a set potentially having duplicates of tuples, and we would like to carry this thing over. So probably the object, also known as tuple, also known as struct, that you see on the slide at this point is part of a bug. So you see the bug being denoted with the blue brackets that we have there, but also the readings attribute is also a bug, which basically means that the order does not matter between all these objects that appear in there. And this in turn is important because sometimes you do want to say when you query data, when you construct data that, hey, I want to produce some collection where the order does not matter. So, hey, query processor, do the best that you can from a performance point of view, and I don't care about the order in which you're going to put the data. All right, so let's summarize what we have seen on the particle data model, and let's see it with another angle. Instead of basically saying, let's start from JSON and see what we can get in to get closer to SQL, now let's see it in the opposite way and say that let's start from SQL and see how we have to expand the SQL type system to get into Particle. And here is the list of the extensions. If you start from SQL, SQL says that the data is a bag of records, of tuples, right? And a tuple in SQL and an object in JSON is pretty much the same thing. All right, so here, and these records have got only scalar values. So here we're basically saying, no, there's more than that. Number one, you may have nesting, right? That is, one attribute of a record may actually be itself an array, a bag, or another, or be itself an object / tuple. Okay. What is the next important extension to SQL? Heterogeneity and sparseness. This is another way, this is actually a repercussion of what Alman described before as the optional schema, and also saying that the data in a collection, be it a bag or be it an array, do not have to follow some rigid structure. You see in the example that we have got here, a very funky version of this. I have got an array, and although all of the elements of it are arrays, once you look inside these arrays, all sorts of things happen. Numbers, booleans, other objects, and so on. Okay, so let's take a step back. What is truly the set of possible particle values that the data model allows? Basically, it is arbitrary compositions of data types, of the scalar types, with the object / tuple constructor, the bags, and arrays. So basically, any way you can compose with bags, arrays, and tuples in all possible ways that you can. And as we said, the schema is optional. And this concludes our data model presentation. So now let's go into a walkthrough of the particle query language. Again, our focus is going to be on nested data as first-class citizens and how a minimal number of extensions to SQL can achieve a whole lot of expressive power simply by composing well with the rest of SQL. All right, so let's start with the most basic and operation, and often the starting operation when we're dealing with nested and semi-structured data. So here I'm going to flatten a bunch of nested data with the appropriate extension to SQL. Let's look a little bit at our input and at our output. So our input here is a collection. It happened to be an array. It could just as well be a bag. And it has got tuples, right? Tuples, also known as objects if you come from the JSON persuasion. Okay. And my tuples have got a readings attribute. And this readings attribute tends to have a value that is an array. And this array contains its own tuples with attribute v. Okay, and then numbers. So now the query that I want to run here is the following. I want to issue a query that says, find the highest two readings in these arrays and output them as basically as a table that, as a collection that is saying, I have records with a carbon monoxide attribute and these values as the output values. So notice here, if you look carefully at the data, it's really the 0.9 and the 0.8, which is the two highest values below 1.0, which is what our query looks. Two highest values below 1.0. Okay. So what is the challenge that we have here if we're coming from an SQL mindset? Well, the challenge that we have here is that these numbers that we're looking to find are not attributes of the top level tuples of my collection, but they are actually the numbers that are found nested inside the readings. Okay, so we'll basically have to get access into the readings. We'll have to, as we call it, flatten this data. So here in green is the very simple extension to SQL's from clause that allows us to do this. Notice that the white part is SQL as usual, so it's basically saying, you know, I have my S alias ranging over sensors, but here comes the interesting part. It says, and I have my R alias ranging over the sensor.readings. Okay, so basically the R will be picking values in the sensor.readings. Formally, extending the classic SQL tuple calculus-based semantics, this is basically saying that your from clause in this example is producing pairs of the aliases S and R, of basically bindings, as they're called, for the aliases S and R. So basically the first binding is the one where the S has bound to the first tuple and the R has bound to the first tuple in the readings of the first tuple. And then the second one, again, the S is bound to the first tuple, but now the R has moved to the second tuple of the first readings, and so on. So basically, the from clause is producing all the combinations that you get out of the from clause entries. Okay, and this is very much, notice what we're doing here. We are introducing a minimal extension that is basically carrying over what SQL was saying in the first place, that a from clause is producing all the combinations that the alias can have over the collections that I mentioned in the from clause. The rest proceeds like SQL as usual. What is a where clause doing? Well, out of all these pairs that are coming out of the from clause, it only keeps those ones that satisfy the conditions. What is the order by is doing? Again, what it's doing in SQL, right? An order by says, I'm getting some data that may not have any particular order, and now I'm producing a particular order. So I'm starting with a bug, and I'm producing an array. And that gets us to the last step, which is, what is the select going to do? Well, the select, what it's going to do is it's going to pack, is the most trivial of steps, it's going to pack my data into the output that I wanted. Okay. Now, this was a very basic example of flattening nested data. You may say that in practice you see many other cases as well. For example, in the same way that in SQL we have the join that says produce pairs of tuples that are matching. We also have the left outer join that says, well, absolutely produce the left-hand, something from the left-hand side, and if you can, match it also with the right-hand side. We need the corresponding feature when we are flattening nested data. So here, let's make a little twist. And the little twist that we are going to make here is going to say the following. I want to flatten, but if I have some readings like this one that we have here, that this reading comes with an empty array, okay, I'd like to have a from clause that will still produce a null for this case, right? That the R is going to come with a null. And this is achieved with the new feature, the left join, the left cross join, because it doesn't have any other condition, where I'm basically saying my R is ranging over the s.readings. Hey, but look, if at some point the s.readings end up having end up being associated with an empty collection, that's fine. I'm going to have the R bind into a null, and eventually, correspondingly, my value out here is going to turn up being a null, as you would expect from SQL. Okay. So we covered so far how we can deal with the nesting that is created by nested arrays. And there is another kind of nesting that we know that we may have tuples in tuples, or as we said, or as you may think in a JSON setting, objects in objects, right? So here we have got this kind of example. So notice here we have put an extra folding, right? We have the readings again, but now the readings have tuples that have events, and the value of the event is itself another tuple. Okay, so my query remains the same. I want to pick these two V's that are the largest V's that are below 1.0. Okay, how am I going to do this? The s.readings as R is doing what it was doing before, right? It was going over the nested array. But now, notice also the red parts, where now I'm saying r.event.v. So I'm basically walking through the tuples, through the nested tuples in order to get to the V, following a dot, an easy to use dot notation, right? So here the extension to SQL is that you don't have to assume that your tuples have a single, that your tuples have just scalars, right? In which case you say tuple dot attribute and you reach the scalar, but your tuple may have other tuples, right? In which case you do this tuple 1 dot tuple 2, and eventually you're gonna do the dot attribute that will get you to the scalar. Okay. Next thing we'd like to discuss here is that these features are nicely now composing with the rest of SQL. So when it comes to new features in the query language, there's really nothing to see here. I'm not presenting any new feature. I'm just giving an example of things that you can accomplish with the features that you have already seen, simply by taking the freedom to blend the unnesting features that we saw with the rest of SQL. Here we are blending it with the SQL subquery feature, right? So here our example says, find all tuples, all top-level tuples that have an average greater than 1.0. So basically, when I'm saying average greater than 1.0, I'm assuming that most of my tuples are going to have these readings, and it's going to have an array, and the average greater than 1.0 is that the values in this array are going to average more than 1.0. Okay, so as we said, nothing new to what's here, right? So my query says I'm having the S range over sensors, And then my condition here is that the average value of the readings, notice the R is reading over S dot readings, is greater than 1.5. Right? So again, we have the new feature that we described before that is basically saying in a from clause I can range over a nested collection, and that's all. Interestingly, these very few extensions in SQL can go a very, very long way. So sticking with the theme of how powerful these tiny extensions to the from clause are, we're going to do an example now that looks very non-SQL. So at this example, I'm saying that my collection of data is really one massive array. Okay, so I'm not even mentioning at this point the collection of tuples that have something. I'm just saying directly, it is my collection is an array of numbers. Okay, and my query remains the same. I want to find the highest two that are below 1.0 and output them as carbon monoxide. And notice here, what's going on here. Now I have my alias R ranging over the readings, and then my where clause says, is the R less than 1.0? Then I'm ordering by the R, and finally I'm outputting it as carbon monoxide. And the key point to notice here is that this R, we removed the restriction that SQL typically puts in aliases. What is the restriction that SQL puts? SQL says, well, the aliases bind to tuples. And here we're saying, no, the aliases bind to whatever, right? And this can be, of course, very often your arrays are not going to be the top level thing being an array of scalars. More often you will have some data where you have an array of scalars nested inside, but the same principle remains. That is, I can have my alias range over whatever. Okay, over scalars, over tuples, over arrays themselves. Now let's change gears. So far, all of the examples were about accessing data that go beyond SQL. What if my point is that I also want to create data that are not SQL, right? And here is a very basic such example. In this example, I start with data that are not SQL, but I also end up with data that are not SQL. So now, noticing the output, that these two highest readings are output as an array of scalars. I'm not saying anymore that the output is a collection of tuples, a table that is that has a carbon monoxide that has these values. No, now I'm going straight into saying my output is an array that has these scalars. This is where Particle brings a more fundamental feature than SQL's select. So, and this more fundamental feature is the select value. Okay, in the interest of compatibility with SQL, we let SQL's select keep its functionality, though really the SQL select is a special case of the select value. What is the select value doing? Basically, the select value says that we're going to be producing here a collection of values. What will these values be? Oh, I think we got a little bug here. Forget as carbon oxide. Here it should be just R, select value R. So it would say it will be whatever you give it to me to be. So if you just say R, you're going to get the scalars. If you had put, let's say, an array symbol around the R, it would be an array, it would be outputting arrays that have the scalars of R. You could actually write yourself how to represent objects slash tuples there by putting the object symbol, the curly brace, and the attribute and value. You could do all of this. That's why the select value is the more fundamental feature that allows you to create any kind of shape. And the select of SQL is the special case of it that allows you to create only tuples. Now, let's go to the following. A question that is very often coming up when we are talking about accessing this schemaless data is, yeah, but what are you going to do with the fact that you may have data that do not conform to what your query has been set up to do, right? A lot of our examples here, we're looking for these numbers, right? The numbers that are greater than less than 1.0. And one may legitimately ask at this point, and what if in the data you find something that is not a number, right? Okay, there's actually plenty of examples of that kind, of things that can go wrong at runtime, because we basically said we have dynamic typing here. We don't have a fixed schema. So things that can go wrong. Notice we had plenty of examples that were having some clause of the kind from collection as alias. A legitimate question there to ask is, and what if I didn't have a bug or an array there, right? If I have a bug or an array, yeah, it's nice. It looks very much like an SQL table. That carries over nicely. What if it's not? Another example. We had plenty of cases where we were saying things like alias dot attribute. You may legitimately ask in these cases, what if this X is not a tuple, right? Or what if it is a tuple and it doesn't have a foo attribute? Okay, so in PartiQL, we support two modes. The so-called strict mode would basically do what you would expect. It basically will crash once these violations happen. The strict mode is recommended for systems where the data also have a schema, right? That is, you may have nested data, you may have semi-structured data, but described with a schema. In this case, the strict mode is nice because since you have a schema, it's good to catch in advance during compilation, basically, of the query that something is off. The next mode is the permissive mode, which is much more convenient when you don't have a schema, when you want to simply investigate your data, right? You have a huge JSON file, you want to start throwing queries at it with what you are the most expected values and types. So in this case, what is happening is that these comparisons that are going to, like in our example, when we had alias dot attribute greater than. Okay, these comparisons that will end up being mistyped are going to lead into effectively a null, right? So, and what happens to a where clause that eventually evaluates to a null? It behaves like a false. Right? So the very first thing that the permissive mode allows you to do is it allows you basically to run queries on big data without these queries failing, right? They will lose the data that are mistyped. What do you do if you want to become more precise? If you have enough of an understanding of your data and saying, yeah, I know that some of the values are integers, but some other ones are strings that I can cast into integers, right? That's where Particle is employing the usual cast functions to cast from type to type, but also introspection functions so that you can check what is the type each time. There is a few more additional features that Particle has, and I'm just going to describe here briefly. At the end, during our Q&A, feel free to ask us for additional details for them, and we have some additional slides where we can elaborate on them. Here I'm going to give the summary. So one thing that people dealing with very sparse objects in JSON or with maps in other systems are finding is that you very often want to arrange over all the attribute value pairs of that you can find in an object, right? And then do some processing with them, check something about the name of the attribute, or basically just pick all of them. And you also want to often do the vice versa. That is, you get some data out from your from and where clause, but you want to basically pivot them. That is, you want to package them. You want to package something that you're getting out of your original data as attribute name and something else as attribute value. This is what the pivoting and unpivoting features of Particle do. Particle, as I hinted with the select value, has the ability to basically create fairly arbitrary new nested and semi-structured structures. By this, when I'm saying new, I mean in addition to the fact that Particle can propagate nested and semi-structured data that I had in my source, simply propagate them out, it also has the ability to create new kinds of structures. And we saw we got a little taste of this when we covered the select value before. And there is more interesting discussions to be had around the role of schema in queries. So this is topics that we'll be glad to elaborate further on, along with other questions that you have either on the few minutes that we will have in the closing today, as well as during our talks actually, because it will be repeated, and the builder session. And with this, I'm going to skip to again to a higher level of the use of Particle as a unifying query language for diverse services. Already, Alman described to you before that we have now multiple systems in AWS that have adopted Particle. Okay. And this is nice because it's providing an integrating data model, integrating query language for querying all of this. And the integration can go one step beyond. So here I have got an example from the Amazon Redshift Spectrum. And the interesting thing about this example is the fact that my data originally are in both the usual kind of SQL tables, in this case in Redshift, but also I had data in some S3 objects. And then I had a query, right? And this query is basically doing a join between the two, between the data that I had in SQL, in an SQL system, and the S3 object. And Particle has been serving this purpose greatly. Keep in mind, Particle says that you don't really have JSON strings here, right? These JSON strings should be viewed as basically Particle logical level objects, and then we have our Particle query saying, hey, I'm format independent, right, and storage system independent, and I'm combining the data that I find in the tables with the data that I find in the S3. With this, I'm going to pass the token back to Alman to discuss further the open source and the future of it.
Thanks, Yannis. So let's talk a little bit about Particle and open source. Particle is kind of interesting because not only do we have open source implementation that you can use and extend, we also are developing the spec. We're not done there yet. So I think it's really important, at our website, particle.org, we have a open source charter. It kind of not only remunerates our tenants, but really emphasizes what we're looking for here. And it's a good way to get on the same wavelength about how we're evolving the language and how you guys can contribute back to it, how you folks can contribute back to it. The other areas of note are we have a GitHub organization that is now modest but growing, and we have a forum. So if you have questions or issues or anything you want to cut, either of those forums are great opportunities to engage. Speaking on specification, this is actually, we do have a GitHub repo for this, and again, the query part is, we have that initial part in place, but we're looking to add, especially with the work we've been doing with Amazon QLDB, the data manipulation side of the specification and data definition side of the specification. But again, even you're able to have pull requests, which we encourage, big or small. So if you want to propose something, this is the right place to do it, or even ask questions or minor type fixes. The source of the specification is LaTeX. So for those of you who've been in CS University or Math University, this might be a muscle that you used to flex. We are using that to specify our specifications, so we look forward to seeing that there. We also have that reference implementation that I was talking about on GitHub as well. And this is implemented in Kotlin for the JVM. And one of the interesting things is, by itself is a useful tool. You can play around with, just download it, play around with Particle, and it's a great way to having customers or yourself get familiar with the syntax and language. But the other nice thing about it is the components are easily embeddable into a Java application, so you can really add query support, take the parser, take the AST, manipulate it as you see fit. But again, we have a GitHub repo. We would love to take contributions and use it and see how people are using it. We're clearly not done. There's a lot of work to be done. So looking towards the future, I think there's an excellent opportunity through our forums or GitHub issues to engage with us. Tell us, as customers, what do you think are interesting things that we should be focusing on? I think we'll value that input very much, and also we'll value contributions here. So questions about how to do some of these implementations, we'd actively love to engage. Other areas, some areas to take a look at are alternative implementations. I know not everybody speaks Java, so having C or JavaScript are some interesting opportunities there. Other open source analytic engine integration, database integration, data formats, and finally any specification work that you want to contribute to as well is a great place to go. So with that, we'll open it up to questions, if there are any. And I think there's a mic here that we can ask. I don't know what sorry, this format's a little new to us, so. Oh, thank you.
Yeah, I was wondering, do you see an applicability to graph databases? For example, having traversals represented as nested, but with unknown number of hops, or is it just not a match?
Did you want to take this one? This is about graph databases. Are we looking to support, or is there support for graph databases in the works?
Yeah, so the present specification of Particle did not cover graphs, but we are actively considering and would be glad to discuss with you.
Great, thanks.
Well, we are already using the Redshift spectrum, and also
sorry, I have a hard time hearing.
Yeah, so we're already using the Redshift spectrum, and we're also using the Athena stuff. So the point is how we're unifying the entire data environment the entire data sources, because when we think about the particle, it's just like just going to one single place and running queries over the entire data lake. Doesn't matter the format, and also I don't know, joining that data with Redshift or something that can be in Athena. I know Athena is a serverless, but it's just like, or maybe pulling something from Aurora or another database, RDBMS. So is that right? But how can we implement it since this is an open source? I mean, I'm just thinking about the services that are available in AWS. So how are you planning as AWS to add more features and try to release one single point of queries or kind of? I don't know if said. I mean, I said a lot of stuff, but so it's just like try to go, and as you can find something like Athena or Redshift, it just go and pick one service and then enable anything. It's just, are you planning to do something like that?
That's a very good question. So Redshift Spectrum has been one example, the first example of a system that has used the features that we saw as a way to deliver a query language that accesses two storage systems, right? The S3 and the Amazon Redshift tables. The particle as a language fundamentally has been made to enable this kind of processors that provide integrated access to multiple storage systems and multiple databases to both make sense semantically and also to be relatively easy and definitely efficient to implement. The discussions that you hinted on of what is the additional systems that may deliver this unified accessibility with a particle is an active discussion going on now, and we would like to actually very much hear from you which are the particular databases and storage systems and so on that you would like to integrate.
Yeah, I think it's important to note that we drive this based on the customer needs. So if this is a need, like this is a great way to engage and see where we can have opportunities for this in the future.
Okay, great. And I got just one more question. So I'm just comparing this to Athena because that's something that we're already using, and I think it's performing pretty well. But what about the performance of this particle? Because when we think of big data, we're thinking of this massive compute and this massive parallel processing. So you said this is not a serialization stuff. So how particle is behaving when you're running on a huge data lake? And is it what's underneath this particle? What's the how the architecture is working to get the best performance?
Performance question,
yeah,
definitely.
So
and you can go to the connector question.
Yeah, I can talk specifically. The reference implementation, we are focused on getting it correct. So this is an ever-evolving aspect of the open source implementation. This is an area that, of course, contributions are welcome, and we're constantly evolving it as we're working on it. Specifically to concrete implementations, this is always going to be a consideration of the service using Particle, right, and how they leverage the components, either open source or otherwise. Right, so it's a logical level, and then that needs to be you can consider it compiled down to the respective, storage engine and so forth. So an example, like QLDB doesn't just stream through all the data; it has to actually do some query planning. And although currently we don't have that as an open source offering, that's something we might contribute directly to in the future. It's just right now we wanted to get it out there quickly so that people can get their hands on it. And this is actually an area you have access to the AST, so you can actually do some of this manipulation and tweak the implementation itself to control the serialization and deserialization.
Okay, thanks.
And one point I would like to add to this when it comes to the performance, look, there is a very well-developed understanding of SQL-based optimization, right? And we definitely had this in our mind when making the extensions to particle, that is, make minimal extensions, minimal changes to SQL, because one thing that we want to keep is all of these optimizations that we know and appreciate from SQL systems.
Thanks for the talk. Particle seems really interesting. A lot of the examples that you were talking about were on data at rest, so in databases and whatnot. Something that my company's been diving a lot more into is infinite streams of data, so Kafka, RabbitMQ, and applying queries on top of that. I wonder if you've thought about the applicability of applying Particle to infinite streams of data and how that might look.
Data at rest versus
Yeah,
streams.
yeah, and so the question around data streams, we actually have an internal system in Amazon.com called Cradle and Dryad that does have streaming, and they've actually utilized our implementation on top of that. So they treated, in that case, a stream as this sort of infinite table, right? And so the query operates on that infinite table, and it works out really well. So I think abstractly that is something we've considered, and it's actually something we've implemented in-house, for sure. Any other questions? All right.
All right, thank you very much.
Yes, thank you, and we
will be